Alright, we're ready for the last section of Chapter 4, which is the conservation of energy. Alright, so we're going to talk about something called mechanical energy, and so this is a little different than what you're probably thinking in your head. Mechanical energy doesn't have anything to do with machines. It actually has to do with the total amount of potential and kinetic energy in a system. So if we take all the potential energy that something has and we add it to all the kinetic energy that something has, we get the mechanical energy. And this remains constant. So like for example, remember that we have been talking about, well, if something has potential energy and it falls, where does it go? Kinetic energy. Well, that's because the mechanical energy of the system is constant. So if one goes down, the other goes up, and if one goes up, the other goes down, vice versa. That's because mechanical energy is constant. So, this is true too. We have to keep in mind that we have something called the law of conservation of energy, meaning that energy cannot be created or destroyed. Okay? So that means that we can't make new energy, we can't make energy go away. What the energy we have here right now is all the energy that we have. We also call this the law of nature. So the total amount of energy never ever changes. And I put a little picture down here to maybe kind of give you an idea. The energy in equals the energy out. So I have a hair dryer, for example. So I plug it in an outlet. That's electrical energy, right? When it comes out, I get thermal energy, which is the heat that comes out of the actual hair dryer. I get kinetic energy. Okay, I get those moving particles that actually, help my hair dry. And then I get that lovely sound that the, hair dryer puts off. All those things are energy. And whatever that energy is, it is completely equal to the amount of electrical energy that came out of the outlet. There's nothing lost, there's nothing gained, it's exactly equal. And that's what the law of conservation of energy says. What comes in, goes out. Equal, equal. So, something else, you can think about this. Think about when you're on a swing. If you're swinging back and forth, eventually you stop swinging, right? You go back and forth. Well, what happens to that energy? Because, if you're moving, that's kinetic energy. If you're no longer going, high, that's potential energy. So technically it looks like you're losing energy. Well, if we look at an actual swing set, some things that we can think of is that with a swing set, you move back and forth. If we stop moving, part of the reason is that, up here with the chains, you get some rubbing up here. And that rubbing is because of friction, good old friction that we learned in the last chapter. And also because of air resistance too. Some of the air resistance causes this to happen as well. We get thermal energy. And thermal energy, of course, is another type of energy. And so that, of course, is where some of our original kinetic energy that we produce with the swing set goes. So there's another example of conservation of energy. Alright, so, power. I've got the power. Hey, yeah. This is the rate at which energy is converted. Right? So, how much power you have. Now, we measure this in watts. Maybe something that you're really used to as far as power goes, I think about like light bulbs are measured in watts. Okay? So, how they get that number is the amount of energy it takes over a unit of time. I call this the PET equation. How do I get PET equation? Look down here. P-E-T. PET. Okay? So you just take your energy divided by your time. Now remember, energy is in joules. Your time will be in seconds. And that gives you your power in watts. And power is actually measured in watts because after the scientist who actually found it, Mr. Watts. Alright, so let's do some practice here. So we have the PET equation. Now, something else that I didn't bring up here, energy. What can be a replacement for energy? Work. Because remember, energy is in joules, work is in joules, and energy is just the ability to do work. So don't be afraid to also see the PET equation written like this. It's very, very common. So we can have P, we can have E or W, because a lot of times they like to use work instead of energy, because commonly what do? We do work. So let's see. To lift a baby from a crib, 50 joules, look right here, 50 joules of work are done. How much power is needed if the baby is lifted in 5 seconds? Okay, so we have 50 joules of work. We did the work in 0.5 seconds. Okay, so this is going to be P, and so we're solving for P, right? That's the only one we don't have. So P is equal to 50 divided by 0.5 seconds. So we just need to take our handy dandy calculator and take 50 and divide it by 0.5, and so that's 100. So P is equal to 100, and so we solve for P, and remember that P is going to be in our units of watts. So you're just going to label it with a W for watts. Because what? Yeah, I went there. It's okay. Alright, so there's the first one. Alright, let's try another one. So P equals E over T, or if it helps you, you could put or W. Okay. So P, E or W, T. Okay. And just be careful about your T's, because if you use capital T, that stands for temperature. So just be real careful about using a lowercase t. Alright, so a runner's power is 130 watts. How much work is done by the runner in 10 minutes? Okay, so I have 130 watts of power. So that's my P. And then they gave me 10 minutes. Now I have to be really careful because, alright, so I'm solving for work. I kind of got ahead of myself mentally. They gave me everything but my energy or work. So, and I have to be really careful because look here at time. 10 minutes. This has to be in seconds. So I have to multiply this by 60. Okay, so I'm going to take 10, I'm going to multiply it by 60. I get 600 seconds. So make sure you do that. If they give you minutes, you have to change it to seconds. If they give you hours, you have to change it to seconds. So make sure you do that. Most of the time they'll just give you minutes. Hopefully they'll just give you seconds. But alright, so P is, oh, they gave us P. So 130 is equal to, we'll just leave it as E, over 600. Now if they give you the T and the P, all you do is take these two numbers, multiply them. So 130 times 600, so you get E is equal to 78,000 joules. Because again, it's energy, so it's a measure of joules. We'll talk about another energy unit later. So there you go. So if you have P and T, it's multiply. Okay. One more here. So again, the equation is P, E over T, or I guess if you need to do W, P, E, T. Okay, so the power produced by an electric motor is 500 watts. How long will it take to do 10,000 joules of work? So power is 500 watts, and 10,000 joules, joules would be energy. So the only thing they don't give you is time, which is good because they're asking how long. So here we have 500 is equal to 10,000 over time. So here's an example of if you're solving for time, you just take and you switch these two places. So basically time is equal to 10,000 divided by 500. So 10,000 divided by 500 is 20. And remember, time is labeled in seconds. Okay, and so there you go. There is an example of how to solve for each variable of the power equation. And of course, you guys are going to probably do some practice of those on your own.